Hello, everybody. We shall see the properties of Fourier transform, very similar to the properties of the Z transform we have seen, and the properties of the DTF, the discrete time Fourier transform. Okay, very similar to that. We have properties here also, using which we can solve the problems easily. Okay, so let's see the properties of Fourier transform. I've not gone to give the proofs for these properties because we have dealt that in detail with all the other transforms. So the proofs would also be very similar to that, and it's detailed in detail. It has been dealt in all the textbooks that we are referring. Fine. So I'll just refer to the properties and the statement of the properties, not actually the proof. Fine. That seems sufficient here to solve the problems, but yes, from examination point of view, you have to look at the proofs also, which are very similar to what we have seen for other transforms. Okay, so let's see these properties. So linearity. What does linearity say? It says that if you have sum of the two weighted signals, then if the transform is linear, then you can do this. What you've done, you've separated the scalar and you've applied the transform only on the signal. How do you say this is a signal, this is not? A is a scalar. See, A and B are not the functions of time, whereas x of t and y of t are functions of time. So we are applying transform only on the uh, signals, which are functions of time, not on the scalar. So scalars can be separated, and we can apply the transforms on the signals. Okay, after that, this is how it is going to look like. Okay, now let's move on to the next property. That's the time shift. See, what is time shift? Where will it be? It would be in time domain. This is the frequency. The right hand side is frequency domain. The left hand side is time domain. So if you apply Fourier transform on the time domain signal, you will get frequency domain signal. That is what you've learned. Fine. Now there is a shift in time. So that shift in time should be in time domain. So what is the shift that we are having? We are having a shift minus t naught. Okay. So this minus t naught shift in time domain should have some effect in frequency domain. What is that effect? Okay, so this shift is reflected by by attaching this exponential. E power j omega is there. Okay, along with e power j omega, it's e power j omega to the power minus t. Understand that? So e power j omega to the power minus t naught. So this exponential should come along with the frequency domain signal when there is a shift minus t naught. Okay, very similar, very similar. This is not new to you. Fine. So if there is minus t naught as the shift in time domain, then in the frequency domain you need to have an exponential e power minus j omega t naught along with the frequency domain signal of x of t. Fine. The frequency shift. The previous property was time shift, which was in time domain. Time shift is in time domain. Okay, the frequency shift has to be in frequency domain. See, omega is the frequency, angular frequency. Okay, so that angular frequency is being shifted by beta. Okay, there's a shift in angular frequency now. That is what frequency shift. So the frequency shift should be there in the frequency domain. So if there is a frequency shift, that shift should be uh, should result in this exponential in time domain. Okay, the time shift also results in exponential in frequency domain. The frequency shift would also result in exponential in time domain. What is the difference? If it is minus beta, you will have plus beta in time domain. Okay, if minus beta is the shift in frequency domain, then plus beta is what you should have in the exponential. Whereas here, if you have minus t naught in time domain, then you will have minus t naught only in frequency domain in the exponential that we have. Okay, so you just remember that. So if there is a frequency shift, that frequency shift should be should result in this exponential along with the time domain. Fine. Now the time scaling. We are scaling the time now. So till now we saw the shift in time, shift in frequency. Now what happens if the time is scaled? See, the time is being scaled. Fine. So what would happen in frequency domain? So it would be 1 by the magnitude. Let this A be a negative entity or positive entity. Here in the frequency domain, it would be 1 by magnitude A. Will not consider the sign of A. Okay, 1 by magnitude A, and this j omega what you have should be divided by A. So it's j omega by A. So this is what's happening with your DTFT also. If you have time scale, if you have time scale, that is reflected here, j omega by A, whatever the scaling factor is there. So that scaling factor should come in the denominator along with j omega. Understand this? Okay, this is not new, okay, something that you have dealt with, so you should not have problems learning this. Fine. Time differentiation. If you differentiate the signal in time, what would happen here? J omega gets attached here. J omega. If d of dx of t by dt is there, then j omega gets attached here. Fine. So this is again something that we have seen in the other transforms also. Frequency differentiation. So here we differentiated the time domain signal x of t. Okay. Then j omega came on right hand side. Okay. Now we are differentiating the frequency domain signal with respect to omega. See, its time domain, it is being differentiated with respect to time. Its frequency domain, it is differentiated with respect to the frequency, that is omega, angular frequency. Okay, so where will you have this? What will happen if you have this differentiation in frequency? So that will result in minus jt in time domain. It is minus jt in time domain, whereas it is plus j omega in frequency domain to differentiate time. Okay, just compare these two and remember that this should help you solve the problem. If you're asked to solve the problem by using the properties of Fourier transform. Understand? And this property is something that we have been seeing, convolution. What is the statement that you can give? The convolution in time domain is multiplication in frequency domain. Okay, doing convolution is a difficult task because it involves a lot of computations. Fine. So that complex convolution operation can be transformed into a simple multiplication problem. Okay, that is where the convolution helps. This holds good for all the transforms you have seen. Fine. So it is true for Fourier transform also. Now, with those properties, we shall also see some important transforms which would help you to solve the problem. We have solved these problems. Okay, just remember the results. Okay, if you have a decaying exponential signal, then it is 1 by j omega plus a. Okay, then you have an exponential whose range is from minus infinity to plus infinity. It's 2a by a square plus omega square. Okay, so these problems we have solved. In the previous session, we have solved these problems. I'm just listing this because these transforms are going to help you in the problem solving. Fine. Now compare these two. These two are there. These two are the same. E power minus 8 u of t, e power minus 8 u of t. So along with this, you have an exponential. When will you have an exponential in time domain? When there is a shift in frequency in frequency domain. So what is that shift going to be? It's plus pi, right? So it has to be minus pi on frequency domain. Okay, so these are some transforms, if you remember, that would help you to solve the problems easily. So let's take the problems one by one. What is it saying? Since we have learned the properties of FT, now we are asked to find out the Fourier transform by using the appropriate properties. So using properties, we need to be doing these problems. So So what type of signal is this? This is a signal which extends from minus infinity to plus infinity. Yes, this t. Okay, this sine 2t is there. This is also there. So there are two functions of t. Fine. So yeah, it's e power minus 3 magnitude t. You keep as it is and express this sine 2t in terms of the complex exponential. That is what is done here. Sine 2t is expressed in terms of the complex exponential. Fine. Now just bring this 2j out and club these exponentials. Fine. There is a bracket here. There is a bracket here. Better you put that. There will not be any confusion. Fine. So it's this exponential multiplied by whole term. Okay. It results in this equation. Call that equation as 1 because we'll be referring to this. Fine, because there are two terms, right? So we'll be rather dealing with these terms individually. Then maybe we'll bring that result in this equation 1. Okay, so name this as equation 1. We'll come to this later on again. We have to be referring to this again. Fine. Now, as we saw, the standard transform e power minus a magnitude t. Why do we need that? Here, this is e power minus 3 magnitude t is there, right? That's why we're interested in this. Okay. Now, since this we know, okay, this can be written as e power minus 3 magnitude t can be written as this. What is a here? A is 3. So it's 2 into 3, 6. Okay. So 3 square it would be 9. So this is what is the Fourier transform of this. Why do we need that? Because we have that here. Fine. Now, along with this e power minus 3t, what is there in each term? This e power minus 3t is there in both the terms. Okay. So in the first term, along with this e power minus 3 magnitude, we have an exponential. So when will you have an exponential in time domain? When there is a frequency shift. So what shift it is going to be? It is going to be minus 2. Okay, so that needs to be understood now. So along with this, we will have a frequency shift. See what is frequency shift? Why we are referring to frequency shift? Because there is an exponential with this. So to understand that, we need to know the frequency. Yeah, there is an exponential along with this. Okay, so we need to have frequency shift. So see, there is an exponential with this signal. We know the Fourier transform of this. Okay, in the Fourier transform of this, okay, if you shift this frequency by minus 2, okay, that will result in this exponential. Okay, we already have this. This is there in the given problem. Okay, so what will be the effect of this in frequency domain? It would be the frequency shift. Since it is plus 2 here, it would be minus 2 here. If it is frequency shift, the sign changes. If it is time shift, the sign would not change. The same sign would retain in the exponential that we have in the frequency domain. Okay. Now, similarly, we have the second term here. Here, this is e power j plus 2t. This is e power j minus 2t. Okay. So if you have e power j plus 2t, this is what it results in. If you have e power minus j 2t, this is what it is going to result in. So we have these two now. So you can substitute these two in equation 1. What is equation 1? Equation 1 is this. Yeah. So we have the Fourier transform of this. We have the Fourier transform of this. So applying Fourier transform on 1, what happens? This would become x of j omega. Okay. This is a scalar. By linearity property, this can be kept out, and we can apply transform on this, which for the result of which we already have. So applying Fourier transform on equation 1 would rather result in this. Very simple problem. This is happening to be a simple solution because we have made use of the properties. Which property? The frequency shift property we have made use of. How did we understand we have to be using the frequency shift property? we understood we should be using a frequency shift property because there is an exponential in time domain. So when there is an exponential in time domain, it obviously is a frequency shift property. Okay, so this is what one should remember. Second one. Okay, so again we have sine pi t. Again we have an exponential. So we have an exponential in time domain. So we can easily understand that again that frequency shift property is going to be helpful. Fine. So sine pi t again express that in terms of the complex exponentials. Okay. Then just club those. Very similar problem, isn't it? Very similar problem. Then we know what is this magnitude is not there. That's it. This magnitude t is not there. Okay, so when magnitude not there, so this is what it reduces the standard transform. Okay, the exponential. Fine. So this is what it is standard transform. Fine. So just hold this term because we have e power minus 2t u of t in both the terms. So this is what it is going to be. So along with this, we need to bring in something. So how do we understand? See, we know the Fourier transform of this. Now, what is the Fourier transform of this along with this exponential? So again, it's a frequency shift property. So there is plus pi, so that should come as minus pi here in frequency domain, and we have minus pi that should come as plus pi. Just substitute these two. Therefore we have called this as equation 1. Okay. Now substitute. Now applying Fourier transform on equation 1 would result in this very similar problem. Okay. You should not have problem solving this. Fine. The third one. Again, there is an exponential, but along with an exponential, we have a t. Let's see how this is going to work out. Fine. And it's not only t that is accompanying the signal, but there is this differential also. So this is which property? This differentiation in time domain property. So if you are differentiating the time domain property, what? Okay, so that property also needs to be used. But let's take the basic ones, okay, as we have done in the first two problems, and rearrange them properly. So they have given all this. Fine. So we will consider one by one, whichever is most basic element, most basic term. We'll take that and we'll move ahead. But before that, what is happening here? Sin t is expressed in terms of exponential. That's it. Okay. So next, x of t. Okay, this is 1 by 2j, right? This 1 by 2j has got nothing to do within this differential. So bring this out of the differential. Okay, and we again have two terms there. Okay, the two terms, these two. Fine. What is common here? It's e power minus 2t u of t is common. E power minus 2t u of t is common. Then you have a t along with that. So t into x of t. So if you consider this as x of t, it's t into x of t. You have t into x of t. So we need to deal with e power minus 2t u of t. Then we need to deal with t into e power minus 2t u of t. Okay, so let this be equation 1. Okay, then let's deal with this and this. Then let's deal with this differential and then bring all the results in equation number 1. Okay, so let's see one by one now. Let's consider the most basic signal, that is this. Okay, decaying exponential standard transform, which we had listed earlier. Fine. Along with this, we need to have the frequency differentiation. So why did they come with differentiation here? Okay, so they are differentiating here. What would happen if they differentiate? Yeah. Yeah. There is a t, right? So there is t here also. There is a t here also in the problem. See, there's a t here. So when can there be a t in time domain? when we go for differentiation property. Why? Here, if you have x of t and Fourier transform that is x of j omega means the differentiating the frequency domain signal will give a t along with this minus j in time domain. So the t gets introduced here. T gets introduced, and anyways we have a differential. Okay, so let's see what happens now. So t is introduced. Okay, t is introduced along with this. Since t is introduced along with this, this minus j t should have also been here. So what is happening with this minus j? This minus j is taken onto the right hand side. It would be in denominator, so that would be taken as plus j in the numerator. So that is what is done. I repeat again. I repeat. This is the differentiation property. Okay. What is that we are differentiating? We are differentiating the frequency. So this is frequency differentiation. So if you differentiate the frequency, it would result in a term minus jt in time domain along with x of t. Okay. So now x of t, if we consider this as x of t, we need to have minus jt here, and that would be, and here it would be differentiated with respect to omega. So that's what's happening. Fine. So the minus j here on the left hand side is taken as plus j on the right hand side. Fine. So if you work out, you'll understand. It's just the observation and rearranging the terms wherever it is required. Okay. Why we took this j here? Because we have t e power minus 2 t u of t here in both the terms. T into e power minus 2 t of t. T into e power minus 2 t of t. Yes. That's why we wanted this. So this is a common term in both the terms we have in equation number 1. Understand? Now, so just differentiate. So differentiation of this would be what? 1 by x being differentiated with respect to x is what? It's minus 1 by x square. So if this is x, okay, so differentiating 1 by x is minus 1 by x square. So it is minus 1 by 2 plus j omega square. Since there is a j along with omega, so that j should come here because they are differentiating it with respect to omega. Understand? So this j and j, it would be j square. J square is minus 1, and so that minus 1 would cancel this minus, and you'll be left with 1 by 2j whole square. Understand this? So this is what is the Fourier transform of t e power 2t u of t. Actually, this differentiation property we could have left easily because this is a standard transform. If you know the transform of this, okay, the transform of t e power minus 2t u of t is just the squaring the denominator here. Okay, this is a little lengthier method. We did this because we were asked to use the properties, right? So we use the properties. Fine. Now, this is something that would be there as the frequency domain in both the terms of equation 1. Okay, then frequency shift again because there is an exponential. See here? In equation 1, we have dealt with t e power minus 2 t u of t, but there is an exponential. And here we have plus t. Here you have minus t. If you have plus t in time domain, it should result in minus t in frequency domain. If you have minus t in time domain, that should result in plus t shift in the frequency domain. So that we shall see now. Okay. Yeah, this is what I mean. If you have plus beta here, that would result in minus beta shift in frequency. Fine. So now we have taken this exponential. Fine. So if we take this, no, not this exponential. This exponential was already there. Now this is the exponential. So it's j t into 1. Okay. So that shift that we need to have here is this beta. See here, what is beta here? It's minus beta, right? So what is beta here? Beta is 1, isn't it? So it will be omega minus 1. Understand? Similarly, you have minus jt. What is beta here? Beta is minus 1. That would come as plus 1 here. Okay. So once we have all this, fine. That equation is still not over because see in equation 1, okay, so we have dealt with these two terms. We have dealt with these two terms. Now there is a differentiation in time. So this also needs to be dealt with. So it is getting little lengthier. Fine. So this is over. Now we are using differentiation in time domain property because we have a differentiation in of x of t there. So that differentiation of x of t with respect to t would result in j omega term in frequency domain. Understand that? Okay. Now it was minus jt if it is frequency differentiation. If it is time differentiation, it is j omega. No minus there. So what happens now? This j omega will come along with the term there in equation 1. So the Fourier transform of equation 1 would result in this. 1 by 2j was already there. So that's a scalar. So this is x of j omega. So along with that, j omega would come because you had the time differentiation. So this j omega is there. So this j and j cancel. So you'll be left with omega by 2. Understand this? Very interesting problem. You have used almost every property here in this problem number 3. Okay, just go through this, solve this yourself. You'll get a fair idea regarding what we're doing. Okay, so what are the properties we have seen here? We saw the frequency differentiation. We saw the time differentiation. We saw the frequency shift. Understand that? So these are some properties that we have used in this problem. Okay. Now let's move on to this. In this, they have not asked us to find out this by the properties. So let's see how it works out. Okay. If this delta function is there, we need to be good with the delta function. What is that? The properties of impulse function. Okay. So let's see how it works out. So the x of j omega, this is something that we are not solving by properties. Okay, so we have taken the Fourier transform equation. Fine. Substitute x of t. Okay, we get this. Okay, this is e power minus j omega, which was there in this equation. So we have got this. Fine. So keep this k function of k out because we are differentiating, we are integrating it with respect to t. So keep only the functions of t within the integral. Fine. Now, what is this? This is a standard term. Where did we see this term? We saw this term in the properties of delta function. Okay. So if you consider this as x of t, and if you consider this as delta, what does delta function says? The properties of delta says delta means it's impulse function, unit impulse function. So what does it say? Using the shifting property of delta of t. Okay, so if it is delta of t, where delta of t exists, we have to evaluate this particular exponential at t where this delta exists. Where does this delta exist? This delta exists at t equal to kt. This delta exists at t equal to kt. So we need to evaluate this exponential at t equal to kt. Understand this? So let it be there as it is, but this is the shifting property. So by shifting property, we are doing this. Fine. So this exponential or any function of t needs to be evaluated at t where this impulse function exists. So this since this impulse function exists at t equal to kt, okay. So this exponential needs to be evaluated at t equal to kt. Okay, this is how it looks like. Fine. So if you do that, t would be written as kt here. That's it. T is substituted as kt. So the whole equation results in this. Now this again coming as some standard form. Okay, the summation we are getting. So alpha has got a function k. This exponential has got a term k. Okay, so that common term can be taken out as the power. So anyways, this summation is going from k equal to 0 to infinity. Right. So take that power, common power out, and this is a standard summation which results in 1 by 1 minus the term. Fine. Okay. So this is not by properties. This is by using the definition of Fourier transform or the equation for the spectrum. Fine. Now let's see the inverse Fourier transform. Fine. In inverse Fourier transform, what would be given? In inverse Fourier transform, x of j omega would be given. Fine. So that x of j omega is given. We need to obtain the time domain signal. That is why it is called as inverse Fourier transform. So how to deal with that? This is the equation for x of t. We are having the equation for x of t because we are asked to find out the inverse Fourier transform. Okay. So bring in this x of j omega here, and when we bring this x of j omega here, you need to be careful about this. The omega, okay, is less than pi. The magnitude omega is less than pi. That means omega is less than pi, and omega is greater than minus pi. That means this x of j omega is this from minus pi to plus pi. So that is what is taken here. So this tells us from where to where we need to integrate. So where this signal exists, there we need to integrate. So where does this signal exist? It exists from minus pi to plus pi. Okay, that's why it becomes minus pi to plus pi. Okay, and this is again a standard term. Fine. So you can write this as an exponential, complex exponential. Again, you will have two complex exponentials, club them as one. Fine, and integrate, which is quite simple. Fine. So after applying the limits of integration, okay, and simplifying that, you will get your x of t to be this. Okay, how do we say this is x of t? This is not x of j omega. Nowhere I've written that. But even then, you can say whether this is x of t or x of j omega. How do you say that? This is the time domain signal or frequency domain signal. Seeing this t, there is no omega at all here. This is not a frequency domain signal. So this is the time domain signal, which we have obtained from applying the inverse Fourier transform to the frequency domain signal. Okay, so this is how we solve the problem. Now, how can we solve this problem? So they have not told us how to solve. Here, see, the form was different. The format is different. It's a signal. Okay. So this is also a signal, but this is in something. This is in a form where we are comfortable dealing with it. Which form is this? Partial fraction expansion method can easily be applied to this particular form, and we are all well aware of that. Okay. So just obtain the factor, just factorize this. So factors are minus 3 and minus 2. So that would be written as like this. So by partial fraction expansion, the same term can be written like this. Find your a and b. That would happen to be 3 and 2 respectively. Okay. And this is now in the standard form. Just apply the inverse Z transform. You'll obtain. Apply the inverse Z transform in this. You'll obtain your time domain signal. Okay. So let's move on to another problem, that is find the inverse Fourier transform by using the appropriate property. Now see here, this is the first problem was using the equation for x of t. The second problem was using the partial fraction expansion. And the third problem is using the appropriate property. You have to find out x of t. Okay. Now for that you need to know this is a standard form. 1 by 2 plus j omega is one standard form. 1 by 2 plus j omega is a standard form. Then 1 by 2 plus j omega square is a standard form. And when would there be j omega here in a frequency domain? You will have a j omega in frequency domain when there is a differentiation in time domain. Okay, so this is all is what is going to help you to solve this problem. Okay, yeah. This is 1 by 1 plus 2 j omega. When will we have that? When we have this decaying exponential. And when will we have this square? When can we have this square? You can have this square to this denominator when you have a t along with the signal in time domain. So that is what is being done. Okay. So when you have t along with minus j, you have d by d omega. That means you are differentiating the signal with respect to t. So this square will not have, this will result in that square. See here? Everybody understand that? Okay. So bring this j onto the right hand side. So it would become j square. J square would cancel this. Very similar problem. If it's t e power minus 2 t u of t is the inverse z transform of 1 by j omega square. Okay, that is what I said. Fine. Now, along with this term, what is there? Along with this term, there is a j omega here. Along with 1 by 2 plus j omega square, there is a j omega. How to deal with that? Okay. So, if you have to have a j omega here, then you have to differentiate the time domain signal with respect to t. Fine. Differentiate that. Now before differentiating, let's just observe. Okay. So this is what is the given signal, x of j omega, right? See the equation. This is x of j omega. So if this is x of j omega, that is the frequency domain signal, obviously this would be the time domain signal. What I mean is this: if this is x of j omega, okay, obviously this has to be the time domain signal x of t. Therefore, x of t is the left hand side signal. Just differentiate that, you will get the time domain. So you can this is what it is. So let's differentiate and let's see what we get. We get this. Okay. So you may have confusions here. So this is the given problem. This is the given x of j omega. This is the given frequency domain signal for which we had to obtain the time domain signal by using properties. So if this is x of j omega, we know that this has to be x of t. That is what is being told. Therefore, x of t is this. Differentiate that. Okay. And obtain your x of t. Okay. So this is what I had to give you regarding the Fourier transform. Fourier transform using the properties and inverse Fourier transform. So with this, the module 4 is completed. In module 4, we have seen DTFT as well as we have seen the Fourier transform. Understand? So this would complete your module 4.